We're going to look at a few more integer properties, and then by next week we'll be able to start talking about cryptography. There's a section in zyBooks called Factoring and Primality Testing, and we're not really going to spend any time in that section within zyBooks. So all that you need to know from that section is what I'm going to tell you right here. Okay, so right here at the end of this slide, you'll know all that you need to know for that section. So first of all, there's many applications that use very large numbers on the order of several hundred digits, and cryptography is one of those types of applications. So consider this integer n below. It's an integer with many, many digits, so that's a very big integer. Now, what if we had to factor that number, come up with the prime factors of that? Well, you might think that there would be an algorithm that would do that, and there could, we can come up with an algorithm, but any algorithm that has been that anyone has come up with is not efficient, meaning that if we have a very large number like this, we are very sure, pretty sure that it's just going to take way too long. Maybe the number happens to be divisible by 2, and that could be checked out. If the number is small enough, you can, just kind of, the algorithm could just check. Is it divisible by 2? Is it divisible by 3? And so on. But as it gets bigger like this, there's just no way that efficiently an algorithm can come up with these prime factors. So that is why this RSA encryption scheme that we're going to be learning about next week, that's why that is such a good system to use, and why it's used with confidence to transmit sensitive information, because what would be behind that, and what would need to be done in order to decode information encrypted that way, would be to come up with these factors for these very large numbers. And again, there's no algorithm that's efficient enough to really make that happen in a decent amount of time. So that's why that works so well. Now, this is really all you need to know from that section called factoring and primality testing, okay? Now, because zyBooks goes into a lot more things, but there's really nothing that I need you to know about from there. It's fine if you want to look at it, but I'm not assigning it at all. So the participation and challenge activities that are in that section, you can just skip those, because I don't have those assigned. So basically, you can just skip this whole section and just listen to what I've just said, and that's really all you need to do for that one section. The next section is called Greatest Common Divisor and Euclid's Algorithm. Now, this is a very important section. We're going to be learning how to do some things here in this section that we'll need to be able to do when it comes to cryptography that we look at next week. So it's really important to understand what we talk about here in this section. Okay, so first of all, let me read what this says here. Cryptographic protocols require computing the GCD of 2 numbers with hundreds of digits, and there's no known way to compute the prime factorization of such large numbers in a reasonable amount of time. And remember, we had said if we had 2 numbers where we had the prime factorizations of those, then it would be easy to come up with the GCD. But this is saying, we can't find those prime factorizations, so especially, if it's a very, very large numbers, if we have very large numbers like that in a reasonable amount of time, we just can't do it. However, if we have 2 very large numbers, there is an efficient way to compute the GCD of 2 numbers. Okay, just the GCD of those 2 numbers. without finding their prime factorization. So it's another way to come up with the GCD. And this is what we're going to learn how to, we're going to learn how to use this here in this lesson. So this theorem, the GCD theorem, says let x and y be two positive integers, then GCD of xy is equal to GCD of y mod x, x. Okay, so what does that mean? Well, here's an example. The GCD of 51 and 24 is also the GCD of 24 and 51 mod 24. Now, we could find 51 mod 24 very quickly. And then we would be finding then, instead of finding the GCD of those two original numbers, we would be finding the GCD of two smaller numbers. And the smaller the numbers, the easier it is to find the GCD. So 51 mod 24 is 3. So if I have to look for the GCD of 24 and 3, that would be much easier than 54 and 24. Now, still finding the GCD of 51 and 24. If I had to find the GCD of 51 and 24, that still would not be that hard. But imagine that you have these two numbers that have many, many digits, and you're trying to find the GCD. This theorem gives us ways to find that GCD by finding successively smaller and smaller numbers to use in order to come up with the GCD. So we can make those numbers smaller, and then it's easier to find that GCD. So let's go through this Euclid's algorithm. Suppose that x and y are large numbers and that x is less than y. Okay, we're going to assume that x is less than y. According to the GCD theorem, y can be replaced with y mod x in the computation of the GCD, right? And the result would be the same. Well, why would we want that? Well, y mod x is going to be smaller than y, and that's the idea, is we want to come up with smaller numbers to work with. So since y mod x is a smaller number than both x and y, computing the GCD with y mod x instead of y is an easier problem. So this is what we do. We repeatedly take the mod function and we continually decrease the values of those two input numbers, and we'll continually replace x and y with smaller numbers. Eventually, the algorithm is left with two numbers, x and y, where y mod x is equal to 0. And at that point, x will be the GCD of the original numbers. Now, this is just kind of the overview of what we do for Euclid's algorithm, but now you're going to see it done. So once you see it done, then it makes a whole lot more sense. So let's use Euclid's algorithm to find the GCD of 153 and 117. So first of all, we're going to write a bunch of numbers all on one line. So start over to the left and write the two numbers that we need to find the GCD of. Write them there at the left and write the largest number first. Okay, so we'll write 153 first and then 117. Now, let's find 153 mod 117 because that, that theorem told us that if we found 153 mod 117, those are using those two numbers that we're starting with, then I can replace one of those original numbers with this new smaller number, 153 mod 117. So that turns out to be 36. Okay, now what we would do is we use the two previous numbers, the 153 and 117, to get the 36. Now what we could say is that same GCD that we're looking for is also the GCD of now these two smaller numbers, the 117 and 36. So now we're going to look at 117 and 36 and forget about 153. Okay, so now we would be saying, okay, 117 and 36, what would the GCD of that be? But we're going to go a step further, and we're going to use that theorem again. And we're going to take those two previous numbers now, 117 and 36, and take 117 mod 36. We'll find that to be 9. That used the two previous numbers, 117 and 36. But now the GCD of 36 and 9 will be the same GCD of those original numbers. And see, we're making it easier and easier here. Okay, now we'll do it again. So we'll use the two previous numbers, 36 and 9. 36 mod 9, that is a 0. Now, what that said in Euclid's theorem that we just went over, and we don't have it here to look at, but it says continue doing this until we get down to 0. And we actually always do get down to 0. So once we're down to 0, then it said that, well, it said X then is the GCD. But here's what I'll say, because we know we've probably in this example lost track of which is X and Y, right? So what you need to know when you do this, if you're not really, and we don't really have to pay attention to what's X and what's Y as we're going through this here, but the number that you get right before you get the 0 will be the GCD. So the 9 is then the GCD of those two original numbers. Okay, so we start with the two numbers, write the largest one first, and then we continually take the last two numbers and do this mod operation on them, and keep getting smaller and smaller numbers till we get down to 0, and then back up 1, because the number that you get right before 0 is going to be the GCD. So we would say the GCD of 153 and 117 is 9. Okay, let's do another example. 675 and 210. So we'll start by writing the largest number first, and then we're going to take those two numbers and take the largest, and then do a mod operation on the smaller ones. So we have 675 mod 210, and that ends up being 45. And we used the previous numbers. We're always using the two previous numbers. So for 45 we use 675 and 210, but then we go on and do 210, use 210 and 45, and get another number. And we're going to continue to do that until we get down to 0. So this next one would be those last two numbers is 45 and 30. 45 mod 30, we get a 15. And then 30 mod 15 gives us a 0. And so we know that the number that we got right before we got 0 would be the GCD. So 15 would be the GCD of these two. Let me say this, as you're doing this, I'm not opposed to you using like an online mod calculator that would perform these mod operations for you. So, you don't have to stop at each one and, subtract as many of, like the first one, 675 mod 210. You don't have to just, by hand take as many 210s out as you can and see what's left. I mean, that could take a little while. So once we get to this point, I'm fine if you want to just like look up online mod calculator, and you can just type in, or even I think even just straight into Google, you could type 675 mod 210 and you would get an answer. So you can try that just some way. Or, you know, if you have a scientific calculator, then you could use, or some kind of graphing calculator, you could get those values. Okay, so now officially, if we want to put this into an algorithm that could be, you know, used by a computer, um, we would come up with something that looks like this. So I'm just going to kind of show you. We're going to kind of go through it, and I'll kind of talk to you about how, you know, what's happening as we go through. So first of all, it says input two positive integers x and y, and then the output will be the GCD of x and y. So first of all, remember we said that y, we should put the largest one first along this line. So this says if y is less than x, swap them, because they're going to be always considering the one to the left to be the y, the one to the right to be the x. Okay, so they have us swap it if y is not the bigger one. So once we do that, now we have the biggest one saved in the y value. So then it says now find r, which is y mod x. So that would again just be the 153 mod 117, and that would give us the r. So that 36 would be called r. Now it goes through a loop here. It says while r is not equal to 0, then do this. What's it going to do? It's going to put x into y, and then it's going to put r into x. So basically, and then it's going to perform that mod operation again. So basically, here's what it ends up doing, what that each iteration ends up doing. It ends up switching those over all one. So, you know, all over one space. So originally we had the y under 153, and now its y has been moved over. And so now y is 117, x is 36, and then we do the mod operation again, 117, 36, and that would be called r. And again, as long as r is not 0, it'll go and do that again. So this gets moved over again. And now r is 0, so we would not do that loop again. And then notice what it says here, return x. And that's the one right before we get the 0. So returning the x would then give us the correct GCD of those first two original numbers. Now, we talked about a theorem last time called the division algorithm, and we basically said, you know, if we've got some integer n, and then we're going to be, and then it says, and let d be a positive integer, that d ends up being what we would consider being the divisor. So basically we're taking n and dividing it by d, okay? So, but then it says that there are unique integers q and r with r between 0 and d minus 1 such that we can write n this way. N equals q times d plus r, right? And the q is the n div d, and the r is the n mod d. So we talked about that last time. So in this example down below here, n equals 13, d equals 4, then we could write 13 as the 13 div 4, which is a 3, times that d, plus 13 mod 4, which is a 1. Okay, so we're going to find that we need to remember that and use this fact here at some point coming up. The next theorem says that we can always express the GCD of two numbers as a linear combination of those two numbers. It says let x and y be integers, then there are integers s and t such that the GCD of x and y equals sx plus ty. Okay, so give any two numbers, the GCD can be written as a linear combination of those two numbers. Okay, now remember that little process that we just went through where we started with the y over, the largest number on the left, then we had the next number, and then we kept finding the remainder, which we called r, by doing a mod operation. We know that anytime we have those three numbers like that, remember we got the r by taking y mod x, so that's how we got the r. But now if you think back to the slide that we were just talking about where we said that given any two numbers, you can, the n and the d, you could write that in terms of n and d and then r in that pattern. It's a little confusing because they used d in that last example as the divisor, but now here we have x as a divisor. But anyway, just know, I guess we can just say this, just know this, that we can always write y as dx plus r, where r is the y mod x, and that's how we're getting that r. And then the d will be the y div x. Okay, so I guess just take my word for that. But now we can reorder that. We can put in, replace r with the y mod x, and we can replace the d with the y div x, and then solve for r, and we get this. R equals y minus y div x times x. Now we're going to be using this a lot, so you're going to hopefully learn this pattern and remember it, be able to remember it. Okay, so each time we loop through Euclid's algorithm, then we can come up with an equation that's expressing the current value of r as a linear combination of the x and the y, right? Because here up above we've got r equals y minus something times x, and y div x, that blue part there, will be an integer. So we see that is a linear combination right there. So each iteration of the loop of the algorithm will be able to come up with this equation that's expressing the current value of r as a linear combination of the current x and y. Okay, so remember this pattern again. R equals y minus y div x x. And so what we're going to find here, you'll see us do it here in a second. We're going to be able to find those certain s and t that we know exist. We're going to be able to find them by doing a series of substitutions using that equation that we can find through each iteration. This r equals y minus y div x x. The algorithm used to find the coefficients s and t such that the GCD equals sx plus ty is called the extended Euclidean algorithm. So we're going to do the same thing as we just did, but we're going to do a little bit more, which is use this equation during each iteration, and then eventually be able to use those equations to find the s and the t. Now you might be wondering, why do we need to find the s and the t? but it turns out that is something that we do need that once we get to the RSA cryptography system. So we're going to learn how to get those. So as I said, to use this extended Euclidean algorithm, we're going to be performing just the Euclidean algorithm, but we're also going to be adding to that, we're going to be accompanying the steps with a set of equations. And then we're going to be able to use those equations then to eventually write the GCD of the two original numbers, x and y. And that's what we need to do. So let's look at this example here. This is one that we just did a minute ago, but we're going to add to it and do the extended Euclidean algorithm. So it says write the GCD of 153 and 117 as a linear combination of those two numbers. So again, we start like we did before. The largest number goes first, so 153 and 117. Okay, and now we're going to find the next number by taking the largest number mod smallest number. So 153 mod 117 gives us a 36. 117 mod 36 is going to give us a 9. And then 36 mod 9 gives us a 0. And we know that we can then step back. The number we got previous to the 0 is our GCD. So 9 is our GCD. And so that's what we've already learned. We know how to do that. But remember, what we're doing now, though, is not just finding that GCD, but writing it as a linear combination of 153 and 117. Okay, so that's what we need to do. So we need to remember again this equation that we're going to be using for several of the steps. And again, it's R equals Y minus Y div x x. And so we're going to start with this 9 here. And remember at one point it was R. 9 was the R because we had just taken the 117 mod 36 to get that 9. Okay, so think about that as the R, and then the two previous numbers are the Y and the X. Okay, so putting in the Y and the X and the R for that step, we would get 9 equals, and then 117 minus 117 div 36 times 36. Okay, so I just used this pattern here, R equals Y minus Y div x x. Okay, so I just did that again for the 9 using the two previous numbers. And then I'm going to step back another time, as many times as I can until I've run out, and this will be the last time I can do it. I'm going to step back and look at the 36 and write it as using those two previous numbers. So 36 would equal, and I use those two previous numbers, it'd be 153 minus 153 div 117 times 117. Okay, so I just used that pattern for both of those. Now we can do a little simplifying here. 117 div 36 is a 3. So now I have 117 minus 3 times 36. And then for the next equation, I can 153 div 117 is a 1. So I have 36 equals 153 minus 1 times 117. Okay, so now remember, so notice that again, for each of those equations, we always use the two previous numbers in that long line of numbers there. Okay, so remember what our goal is, though. We need to write the GCD, which is 9, as a linear combination of those original numbers. So remember, that would be then 9 equals some integer times 153 plus some integer times 117, right? That would be the linear combination. And specifically, we're trying to find the s and the t that would make that be true. Okay, now what we can do though is use those two previous equations that we just found in order to figure out what we can put in here for the question marks. So let's start with the 9 equals 117 minus 3 times 36. That was that first one after we did some simplifying. Now, remember the next equation has 36 equals something, right? So I'm going to then replace that 36 with what I have for that second equation. So I just repeated the 117 minus 3, and then I'm saying times, instead of 36, I'm saying what we had for 36 up here, which was 153 minus 1 times 117. Now, we have to be careful because we're trying to keep the 153 and the 117 there. We don't want to start doing some simplifying where we multiply things out, right? Because we need that 117 and 153 to still be there, because that's what we're doing, is we're trying to figure out what goes in those yellow question marks. So just be careful on that. Don't just go saying, okay, I'm going to subtract 117 from 153. No, we want to keep it separate. Okay, but what we will do is this. We can distribute that -3 that's in front of the parentheses, okay? So the -3 will go be multiplied by the 153, but then we'll also have -3 times the -1 that's in front of the 117. So -3 times -1 is a +3. So I have this. Notice I haven't, gotten rid of my 117s or my 153, which is good. But now I've got a certain number of 117s and a certain number of 153s. That's what I'm trying to find. That will tell us what our S and T is. So we'll just combine. We've got 117 and then 3 of them at the end of this expression. So that means we have 4 of the 117s. And how many 153s did we have? We had -3 of them. So hopefully you see now that we have now written 9 as a linear combination of those two original numbers. -3 is the S and 4 is the T. Okay, so again, we went through our Euclidean algorithm, found the GCD, but we also then, for that GCD, used that equation with the R and the Y and the X to come up with an equation, and then we stepped back with the 36, did the same thing, and then we were able to use those two equations to put together and end up finding out what S and T were. Now we're going to work through one more problem like this. This one will be a little different in that we'll have more than just two equations to put together. So you'll see how we handle this process if there's more than two equations that you come up with. So here's the problem. We're supposed to write the GCD of 675 and 210 as a linear combination of those two numbers. So again, we're going to start that Euclidean algorithm where we put the largest number to the left, then the other number next to it, and we're going to get more and more numbers by taking the one number mod the other number. So we're going to first take 675 mod 210. And remember, you can use some kind of calculator to find that if you don't want to stop and find all these numbers yourself. So 675 mod 210 is 45. Then we'll go on and then look at the 210 and 45 and say 210 mod 45 is 30. Then we look at the 45 and 30. 45 mod 30 is 15. And then 30 mod 15 is 0. So once we get to 0, we know that we back up 1 and know that that's the number that's the GCD. So we know that 15 is the GCD of the two numbers. And so next, though, since we're doing the extended Euclidean algorithm, because the question was to write that GCD as a linear combination of the two numbers, we need to then come up with some equations in order to get the answer to that, to be able to write 15 as a linear combination of those two original numbers. So remember that we have to use this pattern here, where if you're working with any three numbers that are next to each other on this long line, the one to the right would be considered R. The one to the left is considered Y, and then the one in the middle is considered X. So we're going to first start with the 15. We don't need to do that for the 0. So we're just always starting with whatever we got as the GCD and use that pattern. So it would be this: 15 equals, and then the largest number of the 45 and 30, which is the 45, so that would be the Y. 45 minus 45 div 30 times 30. Hopefully you're getting a little bit used to this pattern, and if you use it enough, it'll become very easy for you to remember. Anyway, now what we have to remember is that when we come up with an equation like this, we don't want to simplify everything down, because we would just get 15 on the right, right? We want to continue, we want to keep this equation so that 15 is written as a linear combination of the previous two numbers, which is 45 and 30. So basically what it comes down to, we're always only evaluating just that red part that I have in red, the y div x. In that typed out expression, the part that's red, that's the part we're always going to evaluate, but we're going to leave the other numbers, the y and the x, there. So in this case here, we just need to evaluate the 45 div 30, and that would be a 1. So now we have 45 minus 1 times 30, and then we'll just write that as 45 minus 30. Okay, so we have written 15 as a linear combination of the previous two numbers in that long line of numbers. That's not good enough yet, because we need to write 15 as a linear combination of those two numbers on the very left. But anyway, we're going to step back and now go to 30, just the one before 15, and use that as, pretend that's R, and then so we're going to be working with 30 and then writing that as a linear combination of the previous two numbers, which is 210 and 45. So we'd say 30 equals 210 minus 210 div 45 times 45. And again, it's only that part in the parentheses that we need to evaluate. 210 div 45 is a 4. So we could write 30 now as 210 minus 4 times 45. And notice what we've done is written 30 as a linear combination of the previous two numbers, 210 and 45. Now we're going to go one more and look at the 45. And 45 has two previous numbers, so we'll go ahead and write an equation out for that, treating 45 as the R. So we'll write 45 equals, and then the two previous numbers, so 675 minus 675 div 210 times 210. And again, we'll evaluate what's inside the parentheses. Turns out that's a 3, so we can write 45 as 675 minus 3 times 210. And notice what we've just done is written 45 as a linear combination of 675 and 210. Now remember, what we're trying to do is write 15 as a linear combination of 675 and 210. So far, that first equation, the first time we used that, the r equals blah blah blah, we got 15 equals 45 minus 30. So that's a linear combination of two numbers, but not of the two numbers we want. So we're going to use the next two equations, the one for 30 and the one for 45, in order to rewrite this simple 15 equals 45 minus 30 as a combination of the two numbers that we really want, which is 675 and 210. Okay, so first of all, let's just replace that 30 with what we know it to be. So you see, let me see if I can write on here. I'll make it purple so you can see the difference. So see here, we know that, oh sorry, I circled the wrong one. Okay, let me do this again. We know that 30 is equal to this. So we'll put this in place of 30, because that's the 30 right there. Okay, so we put that in place of 30, and now we see we've got a linear combination, but we're going to simplify it a bit. But our two numbers that are in there are the 45 and 210. So we'll do a little bit of, let's just see that we've got a 45 and then a minus a negative 4. So we'll distribute that minus sign. So we're going to have 45 minus 210, and then that minus a negative 4 becomes a positive 4. So we have that, and we're doing that because we see that we have 45 here that we can still combine. So we'll put those together. There's 145, and then there's 4 more of them. So we have 5 of those. Okay, so what we've done here is replaced the 30 with what we know it to be from that second equation, and then did some cleanup so that we can write 15 as a linear combination of 210 and 45. Now, that's still not good enough. We need 15 as a linear combination of 675 and 210. So now we're going to replace 45 with what we know it to be. Let me use green here. And this 45 right here, we're going to look and see what it's equal to over here. And 45 is equal to, from that third equation, we see that it's equal to 675 minus 3 times 210. So we'll replace this 45 by that. Okay, and once we do that, we see that we've got 675 in there and we've got 210 in there. Those were the two numbers we wanted. So, but let's clean it up a little bit. We'll, distribute this 5 in like that. And so we have 5 times 675 and then 5 times a negative 3. So that gives a negative 15 times 210. And now let's just combine the two tens. We've got negative 1 of them and negative 15 of them. So we've got negative 16 of the two tens. So now we have 5 times 675 minus 16 210. And remember what we started with is just this 15. That's what we that's what all of this that we finally ended up is equal to. So you see that now we've written 15, which is the GCD, as a linear combination of those two original numbers, 675 and 210. So 15 equals 5 times 675 minus 16, 210. And so we would say, remember that, we were, told with that, one of those recent theorems that we can always write the GCD as a linear combination of those original numbers, and we can write it so that, the largest one has an S in front of it, S times 1 and then plus t times the other. So we would say then, if we're looking for S and t, we would say that S is 5 and t is negative 16. So what I'd like you to do is see if you can work through that previous problem on your own. Okay, so write out what you're supposed to be finding, and then try to do it yourself, and then you can look back at my notes if you get stuck, and try that one again. Use my notes to kind of help you along. Then you're going to need to practice it a little bit more. You're going to have some chances to do that probably with the participation exercises, and then probably with the challenge exercise. So go through and spend some time doing this. Remember that it's important that you know how to do this, because we're going to need to be able to do this for when we work with RSA cryptography. So by the time we get to that section, if you've done enough of these problems, then it will hardly be any trouble at all. You'll understand, you'll know exactly what to do, and you'll be able to do it. So anyway, hopefully you'll get some good practice with this. And we're going to stop here. There's still a little bit more in this section to go, but I thought this was enough for you to learn here today. So we'll finish up this section next time, on next week. So officially you'll see that I don't have any of the participation and challenge activities assigned from this last section, but you will be needing to do it eventually for next week's assignment. So you might want to go ahead and get started. It's just that, because you can do it and you probably do want to get started, it's just that you'll get to a point where you're stuck because I haven't told you what we're going to do next time. So anyway, do as much as you can from this last section, the section on let's see, Euclidean algorithm, that one. So try to do as much as you can and get as far as doing problems just like this. But then when you get to something that you can't do yet because we haven't talked about it, then know that you'll be able to finish those up next week, and the entire assignment won't be due until next week. Well, it won't be due until the Monday after next week, so it won't be due for a while. But like I say, go ahead and get started on it. Do as much as you can.